We are on time. This is our session, Intelligent Transportation System and Technology. My name is Brian He. I'm a research scientist at UCLA, and I will be the moderator of this session. Welcome, everyone. And our topic of this session is Intelligent Transportation System and Technology. And we will have 5 great presenters and to present their great research under different topics. So in this session, we will have like 15 minutes for each presentation and following with 5-minute Q&A session. And I will introduce each presenter, and then it's your turn to give your presentation. And for our audience, feel free to type your questions in the chat box and during the Q&A session, and also you can feel free to unmute yourself to ask your question. And I can also like read your questions to the presenters. If we don't have time, we can continue our discussion in the chat box. And during your presentation, I will give you a notification through the chat box when you have 2 minutes left to remind you like the presentation time. Okay, then let's get started. Our first presenter, Runjia, she received her bachelor degree in transportation from ECJTU in 2017 and master degree in civil engineering from Purdue University in 2020. She is currently a PhD candidate and working as a graduate research assistant at Center for Connected and Automated Transportation at Purdue University. Her research directions are optimized-based and AI-based control for connected and autonomous vehicles, traffic safety in mixed traffic, and data privacy machine learning in autonomous driving. Okay, Runjia, the stage is yours.
Sure, thank you. Can I share my screen? Can you see my screen?
Yes, go ahead.
Sure. Hi, everyone. My name is Runjia. I'm happy to be here today and give you a presentation of one of my research named MCPFL, a multi-cloud-based, privacy-preserved, personalized, federated learning framework for steering angle prediction in autonomous driving. So in this presentation, I will introduce it from 3 different folds. So I will introduce the collaboration challenges and briefly a background of what we're doing, and then the benefits of using federated learning in this research. And then in the methodology part, I will introduce about the framework structure, the data that we're using, and the experiment design. And at the end, I will introduce about the result and conclusion about our proposed framework, the performance on heterogeneous data set. So like one of the biggest challenge in autonomous driving right now is the collaboration challenges. So like because lack of standardized live and test data sharing between AV companies is hard to actually develop safety features quickly with repeatable results for the autonomous drivings. As you can see on the left figure, most of the AV companies focused on the West Coast in the California, and some of the companies on East Coast, and very rare in the middle area. So that's why we think that AVs need to be robust with various driving environments and situations, not only focused on the East Coast or West Coast. So that's why we're thinking about maybe we can use a user privacy preserved based framework to help the data sharing, because AV companies care about their user privacy a lot. It's not easy for them to share data with other third parties or other companies. So that's why we're in this research, we're taking care of privacy preserved. One of the method that we're thinking very effective in this kind of area is the federated learning. As you can see on the figure here, on the left side is the traditional centralized learning. we all know that like local users or like vehicles, they collect different data and then they share the data to the cloud. And in the cloud, there will be a model trained. And then after that, the model will be broadcast back to the users and they can use that. However, in this case, the raw data will be shared to the cloud, which will be very dangerous because there are some risk of leaking those raw data. And sometimes the raw data contains sensitive information like geolocations, drivers' characteristics, etc. So that's why like in the federated learning is opposite. The local users collect the data, but they kept the data localized. They only share the parameters trained locally, like using the raw data, instead of share the raw data to the cloud. So in this case, we can actually have the privacy preservation in the federated learning. But in the same time, we still have a global model, which is aggregated by all the parameters shared by the local users. So in this case, we can realize similar performance with the traditional centralized learning. However, one of the common problem of classic federated learning is that it trains a common model, which means that if there is a heterogeneous data set which like has this very different data distribution compares to other data sets, the common model may not perform well on that heterogeneous data set. So in this case, we're actually thinking about how to deal with this because the use case that we're going to have is the steering angle prediction. And we all know that the steering angles on the plain highway and on the hill highway are really different. So in this case, we need to consider the data heterogeneous and also considering like different geographics. So that's why we decided to use personalized federated learning, which is on the top of federated learning to add personalization. So in this case, we can cover the heterogeneous data problem, but also we can boost the data training by sharing the parameters from all the local data set. So in this research, we're using the clustering method to realize the personalization through the multi-cloud. And in the methodology part, I will introduce this like detailedly. So first, what is multi-cloud computing? As you can see on the figures here, multi-cloud computing involves using multiple cloud networks, and they can have the services simultaneously. Like in each cloudlet, you can have a different services, or in this case, we have users with similar preferences grouped and assigned to the cloud, and then this cloud will offer them personalized service. So as you can see on the figure here, if we have similar driving behaviors, like similar vehicles that's like on the similar geographics, if they can share a cloud, so this cloud will boost the training performance, but also because we clustering the similar data set together, in this case, we can train a model like targeting to this kind of geographics. So in this case, we realize the personalization. And here is the our MCPFL steering angle prediction framework. As you can see in the figure, so like basically here are the stages or the steps in this framework. So first we gather the image data from different locations, for example, like on the highway, a plain highway, on the hillway with large curves. After that, we generate the user identities locally. So for each local users, they will based on the raw data they collected to generate the user identities. So the user identity here is the average steering angle and also the steering angles distribution. And then after we get this user identities, we implemented a clustering algorithm to cluster the different local users to different cloudlets. And within each Multicloud cluster, we will train separately end-to-end steering angle prediction model and then share the parameter within their respective private cloud to generate a personalized model, which is also a cluster-specific models for those type of geographics or for those type of local users. And here is the end-to-end steering angle prediction model that we're using. It's a very simple model. We just like input as a series of images, and the output is the steering angle. And the data that we're using in this research is from the Utah City dataset. So in this dataset, they have very good is that they have different geographics already separated. For example, we have 5 different local data set, which is in the driving scene 1 is plain highway, driving scene 2 and 3 is like hill highway with a little bit curve. And then on the 4th driving scene is hill highway with large curves. And then for the driving scene 5, it's still like plain highway. So in the experiment, we have each data set, each local data set split into training and testing. And for the clustering, as I mentioned previously, we have 2 different factors. One is the average steering angles, and the other is distribution of the steering angles. So based on these 2 clustering parameters, we have 3 different clusters here, which is driving scene 1 and 5, and driving scene 2 and 3, and then driving scene 4. So as what I mentioned here, driving scene 1 and 5 are plain highway. Driving scene 2 and 3, they are hill highway with little curves, but driving scene 4 is like a hillway with large curves. So that's why we have 3 clusters here. Makes sense. And then in the training, we have 2 different baseline models. So the first one is the classic Fed average, which also have communications 100 rounds, and then local model training batch size set at 32, which is the same as our proposed model. The reason that we're using Fed average is we want to compare the adaptability of different models to different heterogeneous data sets. And then the other baseline model is the local model, which is highly personalized, adapting specific local data because it's trained using the specific local data. So which means this type of model may be perform best on those local data set because it's trained based on that data set and it's highly personalized. The reason that we're using this local model to compare with our proposed model is also we want to compare the adaptability. We want to see that whether our model performs similar to the local model or not, in order to judge our model is actually perform good in terms of personalization. And so in the training, we have 100 rounds of communication, which is approximately 10 to the 5 training steps for each local model. And in the testing, we're using the RMSE as the testing metrics. And then we apply the our proposed model and also the baseline model to all of the 5 local data set, compare the results, compare the adaptability, and then also the performance. So here are the results. So as you can see in the figure, we have the ground truths, we have our proposed model, local model, and Fed average model. So this is not that clear, but here I can show you some data. So as we can see that multi-cloud personalized federated learning model, which is the proposed model, performed the best. And our proposed model show evident benefits on the data set with different distributions. For example, very like evidently on the driving scene 4, as you can see, the Fed average has a very high RMSE because it's very different data set compares to other 4 local data sets. But our model kind of have the similar performance with the local model, which means that our proposed model has a very good adaptability in terms of the heterogeneous data set. And moreover, our model adapts better on different local data sets. Even like our model can have better performance than the local model. As you can see on the driving scene 2, because driving scene 2 and 3 is what we train together. So in this case, we actually boosted the training because we include more similar data. So if you have only a driving scene 2 local model, you only have the data set from the driving scene 2. But if we have our proposed model, we have driving scene 2 and 3, those two similar geographic data trained together. So it has a chance to boost the performance. So as you can see that our model can sometimes outperform the local model. So here's the conclusion. So our steering angle prediction, is a very significant and necessary task in the autonomous driving. So we proposed this framework to address the privacy issue, and then we address the heterogeneous data set by adding personalization to federated learning. And then, as you can see previously, our model generates user-specific global models for local servers in different clouds, and then it outperforms the classic Fed average and also sometimes outperform the local model. And this is my presentation. Thank you for listening.
Great presentation. You just made on time.
Yeah.
Do we have any questions from the audience? Feel free to type your questions in the chat box so I can read it for our presenter. And during we are waiting, I may have some questions for you.
Okay.
And first one can go to page 4.
Okay. Yes.
Yes, like a very basic question here. You have 2 figures to illustrate the task stat for AVs, right?
Yeah.
And just wondering, what are the difference between these 2? Are they from different years?
Yes, they're actually so from previous years, the AV companies basically located on the west side, like in the California area, but as the development of autonomous driving, more companies located on the East Coast and some of the companies located on the Texas, but rarely in the Middle West or Middle East area. So that is what I want to emphasize, is that even with AV autonomous driving developed a lot, we still have companies distributed in different geographic areas, and also there's no company in the middle of the United States. So if we want to have a robust AV that can drive on under various driving environments, that we need to conquer the collaboration challenges.
Okay, great. That makes sense. And my second question is, so for kind of federated learning, sometimes you train model locally and then you communicate some parameters to the the central the center, right?
Yes.
So I just wondering, under your case, what parameters you are communicating?
Oh, yes. So in our framework, we will first have the data calculate the user identities, which is also local identities, but that is trained, that is calculated locally, and then in each cloud cluster, we will have a end-to-end steering angle prediction model. So this model will be trained on each local users, but also the parameters in this model will be shared to the center cloud. And then the parameters will, for example, have a weighted average. And then like after 100 round, they will weighted average to a common model. And this common model is for this cloud cluster. So the parameter shared is from this neural network.
Okay, great. We got questions from the audience.
Sure.
So I will read it to you. Great
Yep.
work. I see you use CNN. May I ask why only CNN? There are few advanced CNN, and are you planning to use those later?
Yeah, that's a good question. So like previously, we think the focused or the target of this research is just to emphasize the using of federated learning to help conquer the privacy preserved problem and also help with the collaboration challenge. So here we just choose a very simple CNN, very classic structure, but definitely there are more advanced network that we can use. And also here we only use the front image, but we can also use like left side image, right side images. So like in the future work, we plan to add more data and then have like advanced framework to help with this. Yes.
Okay, and following question from the same audience. Is the data available to public? May I contact later to discuss detail about your work? So I think you can answer through the chat.
Sure. Yes, this data is Utah City dataset, and previously they have a challenge on the steering angle prediction, so they actually made the dataset public. So you can search on GitHub. They have a whole page for that, and you can also like contact me. I can type you the website.
Great. I think we have time for one more question, but we got more in the chat box. I will read one. Which will be the parameters to select users for specific cloud models, those they need to be assigned to?
Okay. Can I?
So kind of like a criteria how you select users.
Oh, select users. Is that the like how to cluster the users into different clusters? So basically we have two different parameters to in the clustering algorithm. So one is the average distribution, the other is the average steering angle, the other is distribution of the steering angle. So like when the users have their history data, or when the users right now like driving on a geographic like plain highway, we will collect those data and then calculate the user identities and then assign them to different cloud. Yes.
Okay, I think we are out of time. There's one more question left in the chat. Feel free to answer, to continue our discussion in the chat box.
Sure. Yeah.
Thanks, Runjia.
Thank you.
Okay. Our next presentation is from Ethan. Ethan is currently a research scientist level 2 at TuSimple. He received his PhD in civil engineering from University of Michigan with master's degree in computer science and engineering. His research includes autonomous and connected vehicles, machine learning and AI, multi-agent systems, and predictive science. He focuses on both theories and real-world implementation of machine learning and AI algorithms in transportation systems. His research work in connected vehicles has been tested in real-world scenarios in both Michigan and Ohio, and his research in autonomous vehicles has been deployed and tested in real-world autonomous truck fleets in Arizona. Okay, Ethan, go ahead.
Yeah, thank you, Brian. I appreciate that. Hello, everyone. So let me share screen. Can everybody see my screen right now?
Yes.
Okay, thank you very much. So hello, everyone. I'm Ethan Zhang, and it's great to be here. And today I'm presenting my recent work, predictive trajectory planning for autonomous vehicles at intersections using reinforcement learning. This work was done with my courses, Zhang and Dr. Nathan Masood. So We see great opportunities introduced by autonomous vehicles, but their reliability is still a challenge. So in addition, in transportation systems, pedestrians and cyclists can be more vulnerable because they are not protected with airbags like vehicles. Accurate prediction enables current autonomous vehicles to take more informed actions. But the planning topic itself is very important because planning policies directly determines how autonomous vehicles behave. And for the planning, there are three categories in terms of planning, including route planning, which tests vehicles which route to take from one place to another, maneuver planning, which tests vehicles to turn left, turn right, or going straight, and trajectory planning, telling a vehicle how to adjust its dynamics, such as acceleration profile. So this work focuses on the trajectory planning paradigm. The purpose of this work is to identify a planning strategy, which is a series of acceleration and heading profiles for the subject vehicle to follow in the future 5 seconds. For example, here in the illustrated case, we plan the acceleration and headings for the green subject vehicle to follow in this traffic environment towards its desired place. And this figure shows the overview of the work based on our previous work on predictive models, which includes trajectory prediction and also driving risk prediction. First of all, we have a driving scenario generation module as marked in green here to generate socially acceptable driving scenarios based on real-world data set. And then we formulated the planning problem with reinforcement learning to find better planning policies. The driving scenario generation has two components, including a scenario encoding and a Gibbs sampling-based scenario generation module. Here, the BGM refers to Bayesian Gaussian mixture model to generate or simulate driving scenarios. We train 3 BGM models to encode the real-world driving scenarios, and then use a Gibbs sampling method to simulate socially acceptable driving scenarios. So let's get started with the BGM models for scenario encoding first. In this work, the driving scenario is a 10-second long realization of translation network. Since this work uses a learning-based strategy, amounts of training data are needed. So there are a few public driving data sets that provide samples of driving scenarios, but the number of scenarios available in those data sets are very limited. So we have to do a driving scenario simulation. To maintain the feasibility of driving scenario, a simulated driving scenario should satisfy at least 2 constraints. The first one is an individual agent level. Agent's behavior and pattern should be reasonable. For example, step lengths of pedestrians, acceleration limits for vehicles, etc. And secondly, at scenario level, agent trajectories in driving scenario should be socially acceptable. For example, in reality, traffic agent tends to avoid collisions by nature. So based on these constraints, we propose a driving scenario generation method that use BGM models and Gibbs sampling method. To satisfy the aforementioned constraints, we present a hybrid simulation method. It simulates driving scenarios based on real-world driving scenario dataset collected by a fleet of autonomous vehicles. In a driving environment, mapping information stays constant, so a driving scenario is mainly determined by the trajectory of vehicles, pedestrians, and cyclists within it only. The rough idea is that we sample a number of existing trajectories from agents and reconstruct a new driving scenario based on these trajectories. First of all, we encode the driving scenarios to describe them in an abstract way. For each scenario, we extract all vehicles, pedestrians, and cyclists trajectories, and discard trajectories with the total trajectory length of less than 10 seconds, and build trajectory pools based on extracted trajectories. After that, we train, so here we have 3 trajectories pools for 3 different types of agents. And after that, we train BGM models on top of 3 trajectory pools respectively, and know that a sample in the trajectory pool is a scenario pack. For example, all vehicle trajectories in scenario 1 correspond to one training sample in the vehicle trajectory pool. Based on the BGN training results, we can obtain 3 BGN models. After applying the models to the real-world driving scenarios, we can get an encoding of each driving scenarios. For example, all vehicle, for example, in this case, for the scenario 1, the vehicle trajectories are encoded as component 2, and the pedestrian trajectory inside the scenario 1 are encoded as component 1, and the cyclist trajectories are encoded as component 0. So through this, we do scenario encoding. And after that, based on the scenario encoding results, we use the Gibbs sampling to generate driving scenarios. Gibbs sampling guarantees that the result dataset follows a similar distribution as the original real-world dataset in terms of patterns encoded in the previous step. We assume that vehicles are backbones for each scenario, and patterns for pedestrian and cyclists are affected by the patterns of vehicles. Pedestrian patterns and cyclist patterns are independent to each other because their movement rarely have conflicts, representing trajectory patterns for vehicles, pedestrians, and cyclists as X, Y, and Z. Based on the encoding results, we can compute a conditional probability PY given X, PZ given X, and PX given Y and Z. Then we can initialize the sampling process by randomly sample a desired number of vehicle trajectories from the trajectory pools we constructed previously. And then we can obtain the encodings of this trajectory pack. Based on the encoding, we can sample the pedestrian trajectories and cyclist trajectories based on PY given X and PZ given X respectively. And based on these two sample pedestrians and cyclist trajectory, we can then sample the vehicle trajectories based on PX given Y and Z. The sample agent trajectories, not including the initialization ones, then make a raw driving scenario. Then we do a social acceptance check to remove trajectories that not satisfy the social acceptance constraint. The above result vehicle trajectories is used as the route to initialize the next simulation, and then we keep repeating this process until we obtain the desired number of driving scenarios. So in the driving scenario, the surrounding environment of subject vehicle continuously change. So after obtaining a driving scenario, we need to find a mathematical way to represent it and prepare for reinforcement learning framework. So to model this dynamic environment, we use a graph-based representation to abstract driving scenarios. In the scenario, each agent is represented by a node, and they have different type of probabilities. That's the flexibility of graph representations. So the driving scenario, driving environments may have different type of surrounding vehicles. So first of all, we define a graph with fixed number of vehicles, pedestrian, and cyclist nodes. In this example, we use a graph with 3 vehicle nodes, 2 pedestrian nodes, and 2 cyclist nodes. So in this example, at time t equals to 0, we select the vehicle 1, 3, 4, and pedestrian 2, 3, and cyclist 2, 3 to construct this graph. We selected these nodes mainly based on the predicted location of this agent to the subject vehicle location. As time goes by, this traffic environment changes, and the graph is updated correspondingly. So here at time equals to 1, the node linked to the subject vehicle node becomes vehicle 2, 3, 4, pedestrian 3, 4, and the cyclist 3, 4, and corresponding edges for each node itself are updated accordingly. Note that in this process, we are planning future movements, so trajectory prediction results are used to compute the distance to the subject vehicle so as to update this graph. So the edge weights for the from the agents to subject vehicle are computed as indicated here. For vehicles, the edge weights are determined by the predicted driving risks, as we denoted as R here. and also positional stressor, which is measured by distance to the subject vehicle. The smaller the positional stressor, the stronger it is. For pedestrian cyclists, the weights are meaning distance to the subject vehicle. In general, when conducting trajectory planning, researchers always use reference paths to guide the future trajectory planning of subject vehicles so as to reduce the exploration time, reduce the exploration time, and also avoid some random useless explorations. So in this work, we investigating selection of two types of reference paths. One is human-driven reference paths, and the other one is simply kinematic feasible constant speed paths. So we define an action at time step being an acceleration and the heading adjustment pair to the reference path by discretizing acceleration and heading values. We formulate action sets as shown here with size 451. The reward at obtained each time step is based on positional stressor related cost, and the WT is the edge weight set at the time step as we indicated here. And we take the strongest stress among them. And reward also includes the average ejectness of the plan trajectory so far. So to maximize the reward return, the subject vehicle is led to maintain distance from other agents and high-risk vehicles to reduce exposure to positional stress, which corresponds to safer action policies. So due to time limits, I will just present the proposed PQ network right here. For the details, if you have questions, we can follow up on the chat. So the main idea is that we have a graph, we have a PQ network established here to learn different components of the graph, and then we use the deep Q learning algorithm to train this network so as to get the optimal policy. So we conducted experiments on two non-signalizing intersections, which contains a T-junction and also a Lermogen intersection. The intersection diagram shown here, these two intersections are extracted from the public LIF-L5 dataset, and these are two urban intersections along the autonomous fleet routes. So in this slide, we show the reduction on exploration space when introducing reference paths. Instead of randomly explore the whole region, the region to be explored are reduced to the colored region here. It covers almost the whole lane the vehicle is about to reach. So the reward trends during the model training are shown in the figure. The shaded region, so reward for each training episode, and red lines are the reward trend average every 10,000 episodes. So in this case, we are using human-driven trajectories as reference paths. We can see that for both intersections in the proposed model converges after about 30,000 episodes. Here I show some representative result scenarios demonstrate the model performance. So in this case, we show a subject vehicle driving through scenario. The subject vehicle is on the arterial, is about to drive through the intersection. At the same time, there are two surrounding vehicles which intend to use the same lane as the subject vehicle in the intersection. The red line is planned trajectory, and blue lines are the vehicle trajectory. The yellow lines are the pedestrian, and of course, also for the gray lines are for cyclists, and the green lines are the lane boundaries. So in this case, the planned trajectory generated by the model has the subject vehicle decelerate to let the right turn vehicle complete making the turn. During the process, the vehicle of the subject, the velocity of the subject vehicle changes from 12.1 meters per second to 10 meters per second. And in this case, we are showing the surrounding vehicle is about to pass the intersection from a further distance compared to the previous case. And in this case, the policy has the subject vehicle comes to stop because of the through movement vehicle moving too fast. And also we have in this case, the subject vehicle is about to make a right turn to the arterial. At the same time, two pedestrians are near the intersection, and one of them ends up crossing the intersection within the planning horizon. So the policy has the subject vehicle stop entirely for the planning horizon. We also have a case for the merge case. So here, the subject vehicle merges from the upper lane. At the beginning of the planning horizon, a leading vehicle is ahead of the subject vehicle, and another vehicle is following the leading vehicle in an adjacent lane, as shown here. The plan trajectory has the subject vehicle closing this gap, putting itself ahead of the second vehicle, as the gap is large enough. And the model plan trajectory for the subject vehicle the action is cutting, and during the process, the velocity of the subject vehicle initially increased from 3.8 meters per second to a peak of 5.1 meters per second, and then decreases to 4.7 meters per second. We further evaluate the model performance. We also compare that to we compare the model results against the human driving in terms of three metrics: the safety and driving comfort and the energy consumption. So in this table, we show the comparison results. We show that the result indicates that the plan trajectory performed better than human driven in all investigated metrics. And the table denotes that the proposed model is capable of outperforming human driving with respect to driving safety and driving comfort, and also the energy consumption. So this slide shows the general trajectory planning performance proposed model to the human driving. The two boxes on the top shows the result on the T-junction, and the rest on the bottom shows the result on the land merge intersection. And for each intersection, we are showing the jackness and also the energy consumption along the planning horizon. We see that with the obtained planning policy, we actually have a much better performance on the driving comfort, as we show on the green line here. The blue lines are for the human driving trajectories. And we also see a large amount of energy savings in terms of in these two investigated intersections. We also have a experiment showing the during the selection of different reference paths. Here we use the constant sphere reference path. We found similar outcomes for the policy we learned from the reinforcement learning model, and the land policy also outperforms the benchmark based on the safety, driving comfort, and also the energy consumption. And we see that.
Hi, Ethan. Sorry to interrupt. So we are a little over time.
Oh yeah,
so,
sure. Let me give a summary here. In this work, we propose a predictive framework based on reinforcement learning for vehicle trajectory planning, and also we have simulated social acceptable driving scenarios with BGM models and keep sampling. And we abstract the driving environment in a graph and construct it as a partial observable market decision process. And the model outperforms human driving when planning vehicle trajectories for future 5 seconds in terms of safety, comfort, driving comfort, and energy consumption. I think that's it for just manning for my presentation. And if you have any questions, please let me know. Thank you very much.
Okay, great job. You did a lot of work. So we have one question from the audience. What distance is considered as a surrounding for a certain subject?
What is the distance considered as a surrounding for a certain object? That's a great question. So in this case, we selected the surrounding with a range. So we select about 800 meters away from the subject vehicle we investigated. So it's not an entire system. It's just surrounding like 800 meters nearby.
Okay. Yeah, I may have another question. So I'm curious about the trajectory data used for training. It's kind of simulated data, right?
Trajectories for training.
Yeah, it's like you have vehicle trajectory, bicycle trajectory, and the pedestrian trajectories, right?
Yes. So it's like a hybrid scenario. So the trajectory itself is a real world trajectory, but the scenario is is simulated because the scenario is constructed based on this real world trajectories.
Oh, I see. So you got like historical trajectories from both sources and then use some sampling method to match them to generate your trajectories, right?
Yeah.
And just wondering, like when you generate the trajectories, those data, like the trajectories, are they independently selected?
That's the case. For each type of trajectory, they actually correlated. As we show here, we use a conditional probability to do this selection. So let me show. For the trajectories, for the pedestrian trajectories, it's actually sampled with a conditional probability. And also that's the case for cyclists. And also when sampling the vehicle trajectories, it's also based on the previously sampled pedestrians and cyclists trajectories. So it's not fully random. It's sampled with conditional probability.
I see, that makes more sense. Because if you use real world data, the behavior of both agents, they will have their like a real world background. You will see like the vehicle avoid pedestrian. But if you don't consider such correlation, the scenario generated will be unrealistic.
Yes, right. That's a pretty good point. Actually, that's also a very important point considered in this work, that we want to make the sample trajectories have a rather similar to a similar distribution to the original real world data. That's a point we considered.
Okay, great. And for the audience, we are on time. And if you have any questions, feel free to tap in the chat box. And we need to go to next presentation. Thank you, Ethan.
Thank you. Thank you very much.
So our next presentation is from Jahnavi. She's a master's student in computer science at UT Austin. She received her bachelor degree in computer science and engineering from Mahindra Echo Central, India. She's working on using computer vision and other AI machine learning techniques to infer speed, plate number, and other details from cell phone videos of moving vehicles to identify dangerous behaviors. Prior to coming to UT, she led a team of 9 people at Wipro for a year doing data extraction, validation, and analysis. So Jahnavi, the stage is yours. Go ahead.
Thank you, Brian. Good afternoon, everyone. I am going to present our work on catching speeders via mobile phones and machine learning, an opportunity to improve speed enforcement. So the outline for today's presentation goes in this way. First, I'll talk about the motivation for this project and then present few of the existing automated enforcements that are being used around the world. Then I'll talk about the research gap that we have identified and the methods that we have used to solve this research gap and the results that we have obtained, conclusions that we have made. And I will then present our current work on this project and what will be our future directions going ahead. So the main motivation for this project came from the fact that speeding is a major contributor to the crashes and losses around the world. In United States, around 28% of fatal crashes and 13% of injury crashes and around 10% of property damage crashes are solely based because of speeding related accidents in 2022 survey. So there are many methods that have been implemented to reduce the speeding. Some of them are calming, like road design strategies and speed limits. Some are pricey, like added enforcement, putting police officers on roads to give the tickets to the speeding violations. The other alternative is to use automated enforcement, which is cheaper compared to added enforcement idea. So before discussing automated enforcement for speeding violations, I will go ahead and tell you about other kind of violations that automated enforcement addresses, starting with parking violations. So in this scenario, the systems are installed on law enforcement vehicles and in some of the parking lots to identify the parking violated vehicles. This system that is put on the entrances identifies the license plate of the vehicle and then puts it in a database. This automated enforcement significantly reduces the manual patrol and costs. If you see the bottom right figure here, automated enforcement actually reduces the cost up to 80% compared to the unarmed guards to identify the parking violation. It also saves time and provides detailed records, and it is widely used. We use it here at UT Austin as well, and it is also used in San Jose State. And there are automated enforcements implemented to identify noise violations and emissions. New York, Nashville, and Paris have implemented these smart camera systems to capture the license plates of very loud vehicles. New York has already started issuing fines for this. Paris is still demoing this system. They may start issuing the tickets this year. Coming to emission violations, there have been tools developed to identify vehicles that emit a lot of gas using video analytics and infrared rays. If you see the picture here, there is a system that is implemented in California where they use infrared rays to identify the emissions emitted by the vehicles. And then there is another camera that is added in the system where it identifies the license plate of this violated vehicle. Coming to automated enforcement for red light running and speeding, many of the nations are subscribed to this goal called Vision Zero, where they try to reduce the road deaths to zero and also near zero debilitating injuries. These nations include United States, UK, Canada, some of the European countries, and 8+ Asian countries. Coming to United States, around 22 states and Washington, DC implemented red light cameras in their localities, and 18 states plus Washington, DC has implemented speed cameras in their localities. Coming to Texas in particular, both red light and speed cameras are inactive and illegal to use. So we have seen that there are automated enforcement for speeding. So what is the problem that we are trying to address is that many of the motorcyclists and drivers, they tend to slow down when they see the camera and then speed up again after passing the camera. So this raises the crash issues downstream. So what's the alternative? One can put more police officers on duty for this, but this is extremely rare in time and space. So automated enforcements are much more faster. They can issue more tickets. But as we have seen earlier, it is not enough. So the solution that we came up with is to use cell phone videos provided by anyone so that violators can be identified from any place in the world. To implement this system, we have used a few of the existing techniques in the literature, starting with object detection or vehicle detection. So we have used two algorithms to do this. One is you only look once, YOLO. The other one is region-based convolutional networks called RCNN. Both identify the vehicles. One of the difference in these two algorithms is YOLO uses boxes, grid search to identify the object, whereas RCNN uses segmentation to identify the object and then classify it. After doing object detection or vehicle detection, we also have to do tracking of the vehicles. So we implemented two algorithms for this. One is deep sort and strong sort. These are improvements of the base algorithm sort, whose expansion is simple online and real-time tracking. It tracks multiple objects in real time by combining object detection and data association techniques. So if you see the video, each vehicle is tracked with a number on it. Once objects are tracked, we also need a method to identify the vehicles. So one way to identify it is using a license plate detection and recognition. So for detection, we have used YOLO, and for recognition, we have used the tool EasyOCR. Another way of identification is with make and model. We tried to implement CNN to identify the vehicles make and model. So this is a sample CNN architecture. Our main idea is to identify speed violations. So the general outline for vision-based speed estimation goes in this way. First, video is passed along with other external parameters like distance, actual distance on the road, and other camera parameter, input camera parameters are passed to the detection and tracking algorithm. This system's output is then passed to speed estimation system, where the speed is calculated for each vehicle. The main task in the speed estimation algorithm is to calculate the distance. Two techniques are normally used for this. One is to measure the actual distance. This is normally implemented when the camera is fixed and is not moving. Whereas the vanishing points technique is more generalizable. So whenever camera moves, this vanishing point technique can be used to infer the distance. So our overall architecture is here. First, we pass the input video frame by frame to the vehicle detection algorithm. The output of this is then passed to vehicle tracking. Output of vehicle tracking is parallelly passed through to three other systems. One to do vehicle make and model classification, the other one for vehicle license plate detection, and the other is passed to estimate the speed. In here, once the license plate is detected, we pass the image to a super resolution model because the license plate image extracted is of poor resolution. So to increase the resolution of the image, we pass it to super resolution model and use the enhanced image and pass the enhanced image to a character recognition algorithm to identify the text on the license plate. Finally, these all outputs are then saved into a text file. This is a sample recording of a phone video. As you can see, the license plates are not clearly visible. So the same can be seen in the results. We have tested our license plate model on a Brazilian vehicle dataset. We did this because we could not find any publicly available US license plate datasets. And since Brazilian vehicle license plate data set had similar license plate shapes and also had English text in it, we went ahead with the Brazilian data set. The license plate detection was comparatively good, but the characters in the license plate are not classified well. So it's only 47%. I will tell about the reasons for this in the later slides. We have also tested these models on phone videos recorded in Austin at various speeds and sites. Some of the observations that we made is that whenever vehicle is going under 40 mph speed, the text recognition is correct only when the vehicle's license plate is near the camera. And whenever the vehicles are going between 40 to 60 mph, the license plate model could not detect any text from the license plate because the images quality has reduced drastically. Coming to make and model observation, only make of the vehicle is correctly identified by the ML model, but the vehicle's model is not identified correctly. The same is shown here with some examples. So this picture is taken from a video where the vehicle was traveling with 30 to 40 mph speed. As you can see, the text, license plate text, was identified correctly with a probability of 61% and 28%. Make of the model is also identified correctly. This is another scenario where the vehicle was going between 50 to 60 mph. As you can see, the license plate text is not at all visible. The make and model identification is also not correct in this scenario. Some of the issues that caused this low accuracy is low image resolution, blurred images. This is caused because of fast moving vehicles, and the models that we have used might lack training to its complete extent. So that is also one of the reasons. We did implement super resolution to enhance the images, but that did not improve the classification, text recognition accuracy to what we needed. Coming to speed estimation techniques, we decided to go ahead to use vanishing points techniques to estimate the speed. So once vanishing points are identified, we constructed 3D bounding boxes on each vehicle, and then those are used to estimate the speed. We had to make few assumptions to make the scenario less complicated. Two of the assumptions are that first, vanishing points in each video should be constant. This is possible only when the phone camera is still. The other assumption is vehicle of interest should be moving towards or away from the vanishing point. So what are vanishing points? Vanishing points are points in each image where the parallel lines appear to converge. In this image, you can see this is one vanishing point and this is the other one. Various methods are used to estimate these points, like Huang transform and Runjia algorithms. But the difficulty to estimate these points increases as the image gets complicated. If you see here, the vanishing points in this image are going to be one that is this one, so towards the vehicles. The other one will be perpendicular to the road, the blue line, and the other one will be perpendicular to these two points, so it will be towards the left. So once vanishing points are generated, we use them to create the bounding boxes of the vehicle. So these bounding boxes are generated by drawing the tangents to the car, to the vehicle using the vanishing points. So once 3D bounding boxes are generated, we have to estimate the distance. But distance calculation from the actual video is a very complex process. So first we transform the image into a bird eye view. So we'll have the vertical distance more accurately. So once this transformation is applied, we calculate the distance by finding out the portion of the vehicle that has been shifted from two alternating frames, for example, frame 0 and frame 1. And then we multiply this portion with the actual car length. So once the distance traveled is identified, we calculate speed by multiplying it with frames per second. So for example, in videos that we have recorded, the frames per second was around 24. Coming to results for speed estimation, we have tested our model on a data set called VS13. It has video recordings of 13 vehicles at different known speeds. We did two experiments. First is we used automated vanishing point estimation technique. The second one, we asked users to input the vanishing points. As you can see, the automated vanishing points technique had less error compared to the user input vanishing points, except in one case. We think for this case, the vanishing point estimated by the algorithm is incorrect. That is the reason the speed estimated is very different from the actual speed. These are few other examples of the results that I've explained earlier. As the video gets complicated, as more vehicles come into the picture, the speed estimation results got bad because the vanishing point estimation was not correct. Coming to conclusions, speed estimation is good with errors less than 5% on 5 out of 7 test cases. License plate recognition was improved after using fine-tuned model and super resolution techniques. We needed much more data and much more current data to improve our make and model classification. So we did that later. And we have also observed that errors were lowest when videos are recorded when the videos are recorded for the vehicles whose speed is very less, and they are recorded in a landscape view with a 3-camera phone. So coming to the present work, our new teammate Lamha, she has developed a website that helps us get the videos from the public. So this is the website. One can submit the videos here and know why it is important to catch the violators. She has also been working on improving the make and model classification. As I mentioned earlier, make and model classification is bad because the data the model is trained on is very old. So we needed to gather new data. So far, Aditi and Lamha, they have gathered images, 300 images across 100 make and models from the internet. They are trying to train the model with these images and see if the model can be improved. Coming to future enhancements, we are planning to test with more complex scenarios as in when phone is moving. We are also planning to include more vehicle identification techniques like vehicle color and make and model. We plan to extend this analysis to nighttime videos. So far, we have only tested it on daytime videos. We also plan to develop a mobile application to upload the videos. And then, if possible, extend identifying other violations like red light running, aggressive driving, and dangerous making. if anyone has any more suggestions or ideas on which we can improve on, please feel free to put it in the chat box, and I'm open to questions. Thank you.
Thank you. And you have did like tons of jobs. Good work.
Yes. Thank you.
Yeah. Since we are waiting for audience to put their questions, I may have some questions for you.
Mm-hmm.
And first question is, when talking about you're using like camera videos for your research, right. And when you're talking about the videos, sometimes privacy is the first issue you need to consider, right?
Yes,
it will reveal much more information than you needed, right? And how do you handle such an issue during your research?
So far, we know we will not be able to see who is driving the car because of the layer that's present on each car glass. So we will not be able to identify who's driving the car. And then we also use our university's shared folder to upload these videos and test our models. So we are careful with all the privacy related issues. Did I answer your question?
Yeah, so you did have some like a privacy control, like a protocol for how to using such like videos,
yes,
right?
Yes, we did.
Yeah, that's good. Good to know about it. And my second question is, it seems like you have done like two parts of job. One is, the first is you recognize the plate numbers and also some like car models, all the features, right? And the second one is like speed estimation. Yes. And what is the relationship between these two research?
So once we find the speed of the vehicle, we can, our next step is to put a speed limit, and okay, after if the vehicle crosses this speed, we know it is violating the speed limit. Now, to give the information, if at all we plan to give it to enforcement officers, we need to tell them, okay, this vehicle has violated the speed limit. So to identify what that vehicle is, we had to extract the license plate and make and model information.
I see. So the first study is kind of like support your second study.
Yes.
To recognize the plate numbers and do like following some regulation and management policies, right?
Yes.
I see. And I have a following question here. So for the speed recognition or speed estimation, you may need like a still camera.
Yes.
But for the plate recognition, you may use some like videos from passengers.
No, so we made the scenario less complicated. For now, we only tested with we only tested with the videos that are recorded with the still camera. So we do license plate calculation, license plate inference, and speed inference on the same video, which is recorded from still camera.
I see. Okay, that makes sense. Yeah, for audience who have questions, please feel free to leave your question in the chat box. And thank you, Jahnavi, for your presentation. So our next presentation is from Samiul. He is a recent graduate from Washington State University, Vancouver, and was working as a researcher in the nanomaterials sensor laboratory under the supervision of Dr. Zhang. He completed his undergrad from Pune University of Engineering and Technology, Bangladesh, in electrical and electronic engineering in the year of 2019. He had been a part of the Advanced Intelligence Multidisciplinary System Lab of United International University, Bangladesh, formerly, and worked as a research engineer with Dr. Kodaka, chairman of the CMED Health Limited, Bangladesh. His occupational expertise includes project management, grant writing, experiment designing, hardworking, and mentoring. On the other hand, his research experience contains automation, robotics, machine learning, embedded system designing, and intelligent sensor system. He has multiple research papers and expertise in inkjet printing technology and systems and programming in Python and MATLAB. Samuel, please go ahead.
Thanks, Ryan. Are you listening to me? Is there any problem?
Yes.
And the sound? All right. All right, so I'm sharing my screen right now. Kindly let me know if you can see it.
Yeah, you're good to go.
All right. Okay, welcome everyone to today's presentation on an ID-based navigation control scheme for movable bridges. Let's first discuss about the outline of today's presentation. First of all, I will talk about the importance of automating those movable bridges, followed by the system architecture that we proposed in our work, with all the elements, all the connected parts of this system. And later on, we will discuss about the infrastructure that we designed and implemented it in a simulation environment. And then we applied some key parameters to evaluate the performance of the system. And then we conclude the presentation. So let's begin. Some movable bridges. There are so many movable bridges right now around the world. Most of them are being used for to demonstrate the architectural beauty, but some of them have also been used for real-life applications like ship passaging or different kinds of on-bridge road traffic navigation systems. Some of them, as you can see here, is the London Tower Bridge, the Fort Madison Swing Bridge, and the Woodrow Wilson Bridge. For this specific research article, we actually considered this Woodrow Wilson Bridge, which is a bascule type of a movable bridge, to consider the simulation environment and to design the whole system alongside with that. So why we need automation for this systems actually? So if we see that right now, people are actually controlling those mobile bridges when there is a ship coming. They have to communicate with the ship driver, and then they process all the parts, and they control all the parts to safe passage this ships through this mobile bridges. But this kind of manual handling can cause severe damages sometimes, and there's like so many dangerous accidents happened previously. You know that where there's a human or manual handling, there can be some sort of human errors there, and also we have to consider the work safety of the employees who are actually doing those stuff, because this machineries sometimes they can be heavy, and they are really dangerous if you have to control them from close by. We also have to consider the system malfunction sometimes, because there are so many elements, and we have to make them synchronously, coordinately control to make sure that a ship can pass through the mobile bridge safely. So this kind of consequences can happen if there is a manual handling system. So it is important to ensure implement the automation process for those systems. Due to that, we actually proposed a system where we propose two hypothetical build system, which is actually depending on the bridge and the ship that is coming towards those bridges. We divided our system into three basic parts here to more specifically control all those parts of the system. You can see that for a navigation control for mobile bridge, we have to control the ship. We have to consider the on-bridge traffic systems too, and the actual mobile bridge. So here is the flowchart that you can see, this system is actually a ship-driven system. So when a ship comes, then the system actually, the ship actually triggers the system, and then the automation starts. And it ends when the ship actually passes through that bridge. We also converted the whole system into 3 phases. And in each phase, the ship will pass through different stages of the movable bridge. As you can see, the first phase here is the bridge pre-connection state. So this interface that you can see here, it has been developed by JavaScript, a module named LiftLight. We implemented it, and we actually simulated it using our own parameters that we give. We cannot implement it in a real-life scenario right now. So what we did is we inputted some parameters, and we ensured that those parameters can be controlled by the actual real-life test case scenarios, like the manual velocity of the ship. You can control the timing of the on-bridge traffic and so on. So this is the initial state of the interface that a bridge controller can see in his screen. And here you can see that on the right side of the interface, there are all the basic informations and all the nullification states of the bridge traffic. And we actually considered the maximum velocity of, the minimum velocity of traffic to calculate the nullification time of the bridge. There is a hypothetical bridge that I already mentioned. There are actually 2, but there you can see only one at first. That is the alert bell, which actually designed considering the time needed for the bridge to open up completely, and all the time needed to free the bridge road out of all the on-bridge traffic. Later on, you can see this is the interface the ship driver can see in the screen when it is in pre-connection state. So as you can see, the ship can see actually all the route information and all the communication information for the nearest bridge that he is going to pass. And he can also see the recommended speed that he needs to follow to safely pass through that bridge. This black line or black domain that we can see around the ship is a ship domain that we introduced in our article. That ship domain, in different articles, they actually mentioned that ship domain in different ways, and the measurements of the ship domain is different for different articles. But what we considered is we used a radius of that ship domain exactly similar to the length of the ship, the actual ship itself. So this is phase 2, which is the actual state when the automation process actually starts. As you can see here, there is a current speed and a suggested speed for the ship 2 in the interface. This phase 2 actually starts when the ship domain collides with the alert belt of the bridge. And once the ship domain collides with the alert belt will be constant. After that, before that, the alert belt won't be constant. It will change regarding or considering all the on-bridge traffic and how busy the road is, and what would be the maximum time needed or minimum time needed to open up the bridge completely. So once the ship domain collides with the alert belt, it will be constant, and there will be no change on the alert belt after that. And just right after that, what happens is the ship starts communicating with the bridge itself. So all the bridges' MAC address will be stored in a cloud server from where the ship can find the MAC address, and he can communicate with the bridge itself by sending it the request that I want to connect with you to pass through the bridge. if you see the bridge interface right now, you can see that there is a green circle alongside with the red circle. So the red circle here is the emergency belt. So the emergency belt won't emerge before once the ship collides with the alert belt, and if the disaster speed is lower than the current speed of the ship, then only the emergency belt will form. And the emergency belt will tell you that once the ship comes to the emergency belt or collides with the emergency belt, it shouldn't pass through the emergency belt, because if it continues to pass through the emergency belt, it can collide with the bridge before it completely opens up to pass through the bridge. So this emergency belt, after passing through that emergency belt, the control of the ship will go completely to the bridge part. So the bridge will control the ship. There will be the driver itself of the ship, but the control will be on the bridge's hand to make it slower, to make it safe to pass through the bridge. You can see that this ship here is colliding with the emergency belt right now, and after that, all the connections or the driving control of the ship will go to the bridge, and the bridge will control the ship afterwards. So this is the phase 3, where the ship safely passes through the bridge, and it is the time to reform the bridge and goes to its original form, the initial form of phase 1. So once the ship will pass through the emergency belt of the other side of the bridge, then the reformation will happen. If the ship thinks that he will stay inside the emergency belt for a certain time, there would be some sort of fine implemented, which we included in our paper, that how this fine and this act of not going through the, or not actually managing the law enforcement here. So yeah, that would be the phase 3. And after that phase 3, the bridge would be ready for other incoming ships afterwards. This is a performance evaluation. As we already said that this is a simulation study, and we haven't applied it in a real life case scenario, but what we did is we inputted some parameters to our simulation, and we controlled the ship, and we saw how the alert belt and the emergency belt actually forming. So there are 3 test cases that we provided here. In the first case, there will be no emergency belt formation, because the current speed of the ship and so the steady speed of the ship is fairly equal. The second one, in the second one, there will be a formation of emergency belt, because as you can see that the ship is on the higher speed than the suggested speed. And on the third one, you can see that the speed is actually pretty lower than the suggested speed, so there will be no need of forming the emergency belts here. To conclude the presentation, we actually tried to implement a complete automation system, and we designed a system that incorporates all the elements like the on-bridge traffic, how the speed will monitor, how we can control the ships so that we can ensure the safe passage. We also described 2 hypothetical belts, which is a pretty new concept. There was no other work that has been done in this domain, who actually demonstrated it using those belt systems and those phases to control this whole process, which is clearly understandable and also pretty simple to implement. Also, in this process, the modules that we actually considered, we don't have to do very expensive modifications to our existing system. What we can do is we can incorporate some modules like GPS tracking and other IoT devices existing ships and bridges so that they can communicate with themselves, and all the systems can be controlled automatically. Like all the mechanical systems can be controlled as they are right now. So there will be some motoring actions and some switching actions too, but they will all be similar to the current state. We will just make the system smarter and automatic regarding the ship coming and going. Thank you very much. And if you guys have any thoughts, please let me know. Thank you.
Thank you, Samuel. You have a very interesting topic concentrating on the movement of the ships and bridge.
Yes.
Yeah, let's wait for our audience to put some questions, and I may have some question for you from the transportation, ground transportation perspective. So as the figure you showed, you have a bridge connect traffic between two banks, right? So I'm just wondering, when you are operating the bridges, you may interrupt the traffic. So do you have any coordination between maybe, for example, traffic signal or entrance at the bridges to make sure you can minimize the interruptions to the traffic?
Yes. So this alert belt, when I talked about it, this alert belt will form regarding the on-bridge traffic speed and how many traffics is currently inside this bridge. So there will be some sort of metering actions, like the speed meter that will measure the minimum speed of a car inside of the bridge section. And also there will be cameras which can count the on-bridge traffic, the actual traffic. And with this information, we will see that what would be the minimum velocity and what would be the maximum time to make the bridge nullified so that it can start, opening up. So there will be some, barriers when the ship alert belt will, the ship domain will coincide with the alert belt, then the barriers will operate, the barriers will be activated, and those barriers will stop the on-bridge traffic flow, and there will be still some traffics in the bridge. So we will consider those on-bridge traffics to actually form those, to actually make those suggested times for the ships to come and the emergency belt formation. Yeah.
Okay, that's great. And my second question is, your bridge and the ship will have communications, right?
Yes. And
when you are doing communication, do you consider any cybersecurity issue? For example, if you have some fake signal and fake communication with the bridge, how should you handle that?
Yes, so this section, by the way, is to the cybersecurity domain, so we haven't considered it here. What we actually considered is the actual system that is working like a flow chart. So we haven't considered the IoT security here, but yes, it is a very good thought, because yes, there will be so many fake communication controls and fake messages to the bridge to start the operation or something like that. But yes, it's really important one. But we haven't considered it in this article, but we considered only the flow of the navigation control. So, yeah.
I see. Okay. Yeah, thank you for your presentation. And anyone has questions, please tap your questions in the chat box. And thanks, Samuel.
All right.
Let's move to our last presentation from Yantao. So Yantao is a computational transportation engineer at Argonne National Laboratory. Yantao received his master's degree in transportation engineering from Imperial College London and his PhD in transportation engineering at the University of Texas, Austin. Before joining NIL, he worked as a postdoc at the National Renewable Energy Laboratory. His research focuses on network simulations and travel demand forecasting, including anticipating the impacts of new technologies and sustainable transportation systems, automated cars and trucks, shared automated vehicle fleet and electric vehicles. So Yantao, please go ahead.
Can you hear me okay?
Yes.
Okay, great. Not sure if just 1 second.
I think you are the co-host, so you should have access to share.
Is it up?
Okay, good. Yeah, I can see
Okay, cool. Hello everyone, thanks for joining my presentation. This is the work that I did when I was at UT Austin with my current colleagues at Argonne National Lab. It is about the agent-based simulations of shared autonomous vehicles, but with a focus on the vehicle traveling party size and like seasonality of the travel demand. Yeah, as I just mentioned, there are like two key components in travel demand predictions. We have like a lot of existing models about travel party size and seasonality, but like they are really considered in most of the agent-based simulations. And under this condition, the shared automated vehicle fleet operations, thus like they do not capture realistic ride sharing options. So in terms of the party size, like the average vehicle occupancy can be different because like each person in the travel party should occupy 1 seat, and trips made by a party size larger than 2, they sometimes like fail to be served because there are limited seats in a vehicle. And also, most agent-based simulations, they are just over 24 hours, and they usually do not reflect seasonality or travel day or week. So this week we kind of look into the details of this, and we conducted agent-based simulations in the 6-county Austin region to explore how the key metrics differ as we consider the travel party size and seasonality. And these two things are reflected through the National Household Travel Survey, and we adjusted the travel demand tables for the use in the agent-based simulations. Yeah, the first thing that I want to mention is the National Household Travel Survey. It is the Americans' daily travel samples are collected from April 2016 to April 2017. And this data set has detailed demographic information of households and their travel history on a particular day during the survey horizon. And yeah, it is a good source that can reveal like year-round travel variations and trip characteristics. So here is like a figure showing the variations between the weekday and the weekend, and also different times of day. We can see, and also the different colors are showing the amount of travel by party size of 1, 2, and 3, and 4. We can see that like for the weekdays, we have like more people traveling alone in contrast to the weekends, where we have more people in party size of 2, 3, and 4. And people also tend to travel alone like during the night compared to earlier in the day. And yeah, the second thing I want to mention is the agent-based simulation that we are using. It is called Polaris. It is C++ framework that can simulate most of the regional populations like 100% in really low runtimes. It is an end-to-end travel demand simulator that provides start with a population synthesizer that fits the agent population characteristics. across several characteristics to the regional across tables iteratively. And it has like a series of like travel behavior models to generate a schedule and plan each agent's travel. And destination mode and route choice is also conducted to have like 24-hour day plan for each person in the simulation. And also for the operations of shared automated vehicles, we have dynamic ride sharing that considers the vehicle location and directionality of trip requests. And we have the control of all the detours imposed on all the traveling parties. So with the NHTS dataset, we were able to reflect the like seasonality in the travel demand table. And we assume that like the annual average is 1, and then we apply factors to the trips for different seasons to run the model. And for the weekdays versus the weekends, we assume weekdays is 1 for a season, and then we apply adjustment factors to the weekend to reflect like the change on different days. And to reflect the seasonality, we only and also the travel party size, we use the auto mode that we usually use, which is a collection of the mode of car, SUV, van, pickup truck, rental car, and also the TNCs in NHTS data. So yeah, so this table shows the factors that we applied for the seasonality. And for the party size, we replaced the single person trip, which is like a record in the trip data table, with a realistic party size to that, and also adjusted the all the trips so that the total person trips are somehow mimic the case in the earlier situation. And then we have 4 seasons of year, 2 types of days, as I just mentioned, and also 6 times of day. But we don't have any variations by variations in the party size by trip distance, purpose, or destinations because of the like limited size of the data set. So and since we are doing a cross-section table, so we are not able to consider like more factors in the party size generation. And again, the auto mode is a collection of the modes that I just mentioned. And also we are ignoring the party size over 4. So we only have 1, 2, and 3, and 4 for categories of party size in our simulation setup. Yeah, so this is how we do the cross-section table of different seasons, departure time, weekend versus weekday, and 4 types of party sizes. And based on the share of the person trips, we are we kind of duplicate all the person trips to make it a party size trip to replace the original person trip table. And here is the study region. It is the 6-county Austin network. There are about over 22,000 links and 17,000 nodes. And yeah, we have about over 2,000 traffic analysis zones in there. And yeah, and the figure that I'm showing here are the includes all the activity locations, the links, and the zones that we are using. And yeah, so some other things to mention is the TNC service in the Austin area for the base case is just 1.5% of all the region's travel amount, and we inflated to 10% to be the shared automated vehicles travel demand as a future year scenario. Yeah, so the Austin's 1.9 million population making about 530,000 person trips is simulated under 2 hours using about 40 gigabyte of memory. So yeah, so the base case the base case without considering the seasonality or the party size is that we used 15,000 SUVs, which served 93.5% of single person calls, and they averaged about 28.7 minutes for the whole ride service time. And there is like an average vehicle occupancy of 1.61% during the revenue surveys. And yeah, for comparison in terms of this case, we are comparing the scenarios with party size considered and to the non-party size scenarios. We can see that since we are bundling all the person into the party sizes, we have like fewer requests in that sense. So we have like a higher service rate, and also we have like a drop of total travel time about 5 minutes, and also a 1 minute shorter for the wait times. And yeah, because of the same reason, we have about like 1/3 reduction in the empty vehicle miles traveled. And also we have like a big increase in the average vehicle occupants that we can see. So originally that like those vehicles need to detour to pick up more requests along a trip chain. But now these vehicles are easily to be filled up because of the realistic party size that we consider. So we have fewer party trips throughout the day, and also these vehicles are able to serve more person trips. So we lost a few requests in this case. And if we look at the fleet performance by different party sizes, you can see that we have like more requests in the weekdays for the smaller party size, but during the weekend we have more requests for the larger size of the parties, like 3 and 4. And another thing you mentioned about the wait times or the travel times, we kind of have similar vehicle or fleet performance for party size of 1, 2, and 3, because we always have like detours for those trips. But for the party size of 4, a request that can directly fill up one vehicle, we have about like 1 or less 1 minute wait time for them, and we also have like fewer travel times because of no detour for these trips, because they don't need to pick up or drop off other passengers along the way. And yeah, the last table that I want to show is for the person miles traveled. If like for the weekend, the party size of 2 contributed to the like most or the majority share of the person mile traveled. So this is like a big thing to note, because if we only use the travel demand for just party size of 1, we are kind of like ignoring the situation that party size of 2 is actually contributing the most for the person miles traveled. And yeah, and for the comparison between weekdays and weekends, we have more empty vehicle miles traveled during the weekday because people are more likely to travel alone in weekdays. But yeah, when people are more likely to traveling together, we have lower share of the empty vehicle miles traveled contributed by smaller party sizes compared to the large party sizes. And yeah, so I have some other results, but yeah, these are the results that I want to highlight. And this is just to highlight the importance that we would need to consider the party size and seasonality in many of our research work, and that they usually play an important role and impact our results to a large extent. So yeah, to be specific, we have like a 8.5 increase in the service rate. We have 5 minutes total journey time savings in the travel and wait times, and we have 30% less empty vehicle miles traveled and 28% higher average vehicle occupancy on weekends. And summer and weekdays offer less demand, so the fleets are more idle and able to offer higher service completion rates. And yeah, we didn't see much variation in the weekdays compared to the weekend. So yeah, they are more equally distributed across all the 4 seasons. And the weekends, we have more people traveling together, more groups of 3 and 4 compared to a group of 1 and 2 persons. Yeah, and that leads to low average wait times and travel times. And yeah, and this is also something that I've just mentioned. Yeah, so the last thing that I want to highlight is the party size of 2 are contributing to most of the PMT in the during the weekend. So yeah, this is basically what I want to talk about. Just the importance of reflecting the party size and demand variations to better appreciate the fleet performance. And yeah, and that's all. Feel free to ask any questions or yeah.
Great, thank you, Yantao. The topic is very timely. Like the shared automated vehicle will be like a very important mode in the future. I may have some questions for you here. The first question is, so for the household travel survey, you are using national one, and you got the seasonality and like weekend, weekday variations. So I'm just wondering, like for the household travel survey, what kind of data you have? You have the trip from 1 year so that you can get the seasonality from it.
Yeah, it's the yeah, it's a 1 year survey, and like each household is designated to a particular day of that year, and they will record the exact place that they go. So it's kind of it's not like a household over a year, but they are just a random sample that we picked by the demographic distributions, but they are finally weighted to represent like a year-round travel pattern.
Yes, that's good to know.
Yeah.
And for that, so you have the demand adjustment factors about like a weekday, weekend, and the seasonalities. And just wondering, for that factors, it's like a generic factor you apply for the whole network.
So that factor is used to control the conversion from the person trips to party trips. So originally, we assume that like, or the base case for comparison, we assume that each person will be a party. And that is like kind of an averaged situation without considering seasonality. And when we do a summer, like a scenario for summer, we inflate those person trips to party size trips so that the final distribution will follow the factors that we come up with. Like we have like maybe more trips on weekends and fewer on weekdays, or yeah, something like that, to reflect the party size distributions and the total number of trips for that season.
Okay, so in that way, you kind of like inflate the single trips to like party trips, so that you can make sure the total trip will follow the distribution you got from the travel survey. I'm just curious about like how you handle such like trip variations.
Yeah, so there are like, so I did not put the technical details of the conversion in this presentation, but yeah, we do have that in the paper. We look at each trip record that we synthesized from the agent-based simulation, and then we assign a party size for that. And so we convert one person trip to a party size trip, but in that case, we are dropping some other trips because we need to control the total person trips in the system. And after this kind of conversion, we want to make sure that like we want to make sure that we are following this trip table, saying that the party size of 1 on weekday at AM peak in spring will be 57.6% of all the person trips. So that's how we control such kind of situation.
I see. Yeah, so the adjustment is more on the demand side. And once you got the trips aggregated or like inflated, then you just put them into the simulation to get the real operations, right?
Yeah.
Great.
Yeah, actually.
Yeah. Maybe one more like minor questions. I saw in your VMT calculation, you have a eVMT. Does that mean you have some like electric vehicle in your service fleet?
Oh yeah, so that means the empty vehicle miles travel. So we are using shared automated vehicles. So there are like deadheading vehicle miles travel to pick up requests in that case.
Okay, got it. Thank you.
Thanks.
Yeah, I think that's all for today's presentation. Thank you everyone for participating in our session, and thank you everyone thanks for every like presenter's work. You did a really good job to present